Hi everyone, my name is Salman Ahmed. I'm currently working as research associate and senior data scientist in computational biology research lab. And in parallel, I'll be starting my PhD in electrical engineering from Texas A&M University in this spring 2022. And in my team, we have Harsha bin Natif. He's also working as he's working as research assistant, and Mohammad Bilal. He's also research assistant, and then we have director of our lab and director of our whole university campus, Dr. Haman Naveed. And our solution is called like PRNet, Progressive Resolution Based Network for Radiograph Based Disease Classification. Okay, so here's some simple analysis. We have three unique classes: normal, pneumonia, and COVID. And the distribution of classes is, I guess, shared by previous people. Normal, we have 7,000 plus samples. Pneumonia, we have 4,000 plus samples. COVID, we have 5,000 plus samples. Image quality was good enough, good enough resolution. So, like for any type of problem solving, I guess, for neural networks. Okay, so my training configuration was we used PyTorch and cross entropy loss. We trained for 20 epochs max. Our batch size was 16 for every experiment. We used Adam Optimizer. Our augmentation was horizontal flip, random brightness, random contrast, blur, median blur, and all these augmentations. And we used early stopping for like with threshold of 5. And then we used cosine annealing scheduler for each epoch. Uh, on left we have plain images, and then there is a batch of augmented images on right side. Okay, so my solution is actually based on a technique that was shared by Howard Jeremy in his classes of fast AI. And the technique, it's a modified technique, but it's kind of similar to that one, and he used that to win a competition in ImageNet. I remember like once he talked something like that, or it was an idea but not properly implemented. So I trained it here. First of all, we train our neural network on small images. For example, 256 by 256 that we did here, and we train on that. So it's kind of like our neural network learn bird's eye view feature of the image, like global features of the image. Then we gradually, okay, for example, when first we train for 20 epochs, then we stop here, and then in the next we train with 380 by 380 images on the same backbone that is efficient at B5. Okay, and then we gradually increase size of our images, 460, then we go to 512, and then we go to 640. So by doing this, our model starts to learn like fine tuned based on like we fine tune on larger images. First we tune on this 256, and then we train 380, like the same model that was that was trained on 256. So it's like that. And another concept that we use in our final solution is bias adjustable softmax. So it's not just a simple softmax. We have a probability on it, like have a power on it, or you can say exponent on it. So it what it does, it adjusts the skewness of the probabilities. So it's kind of similar to weighted cross entropy loss, but it's it's after training, like it's in post processing kind of thing. So it modifies the exponent of softmax. So for example, if my predicted probability is 0.3 and my p is 1, then I would say my really probability is 0.3. And if my p value is equal to 0.1, uh, then 0. Like the same 0.3 would become 0.8. And if my p is 2, then the same 0. Then 0.7 can become 0.49. So it actually adjusts the skew of the probabilities, or the skewness of the probabilities that are predicted. So it kind of change, you can say, the distribution of my neural network after after its prediction. Okay. So we have like we designed a simple heuristic to uh, we have a simple heuristic to find the exact p, or you can say the best p that we can on that softmax. And it fits on based on our training data. So what we do here, we take, for example, number of classes is equal to c, and by default we set our search space from 0 to 5 here, and we set m to 5, and we iterate for each class. Okay. And then in each class, we get the probability distribution of that class from our from our prediction. And then we get the training distribution for that selected class, and then we iterate from I to m. And this algorithm, and we shared the code, I guess, on GitHub as well. So it's in this we check, for example, if the probability distribution is close enough to our training set distribution, then it's okay. Otherwise, we kind of iterate till we find the best p. So at infinite time, what we have a chest x-ray, and we resize it to 640 by 640 and pass it to our backbone, and then we get the features and all this. And at the end, instead of a simple softmax, we have this bias adjustable softmax. And these 1.6, 0.4, and 1.0 are the p values that we find from our training set. And then we take the maximum probability and we get it to prediction. And at inference time, by using GPU, RTX 3090, inference time is 0.034 seconds, and on CPU it's 1.14 seconds. These are the results. So at first we started using efficient at B0 for all the experiments, but it kind of seemed to underfit. So seem to underfit, or like we try to increase our increase size of our model efficient at b0, because in progressive resolution at last iteration we have our 640 by 640 images. So I guess efficient and b40 is big enough to handle that resolution, and b0 was small. And here we have our winner model, and it achieved 96.33% test accuracy and 97.99 on 5-fold validation. So from these experiments we concluded two things. One is that, like, in some cases, especially in where some minute information and global information is important for us, so it's better to train on some global level features, and then gradually go to detailed features. And it's kind of inverse to, you can say, uh, like uh, dilated neural networks. And other than that, we have probability adjustment, and it kind of works, especially if in training set we have a little imbalance in our classes. And that's it from my side, I guess.